तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We saw various aspects of nonlinear finite element analysis. What are the type of problems that can be solved using nonlinear FEM? In that process, we recognized certain very important things. One is that when we do a problem, of course, we have to decide whether we are going to do stress analysis problem or whether we are going to do heat transfer problem or fluid flow and so on. That's a very simple aspect. But once we decide that we are going to do a stress analysis problem, the first thing we have to do is to recognize what is the type of analysis. So whether you are going to do a static analysis or whether dynamic analysis, that depends of course on the problem. That's the first thing that we have to decide. Now it's not a very easy decision. Many times certain dynamic analysis you may have to simplify using static analysis, and many static analysis problems can be very easily done using dynamic analysis. So it is not that it's a very straightforward decision many times. Of course, you can do it, you can say for certain class of problems you can definitely say that they are dynamic or they are static. But certain class of problems, though it may appear to be a static problem, so for example many of the metal forming problems are today done or carried out using dynamic analysis, dynamic explicit analysis, basically because you also have to consider certain problems that may arise during static analysis. So you have to know theory of nonlinear finite element quite thoroughly in order to make that judgment how you are going to do that. So once you decide what is the type of analysis you have to do or you are interested in, you also have to look at whether the problem is going to be a small deformation problem or a large or finite deformation problem. That's the next thing that you will decide. Then afterwards you will decide what is the material property that you will use. One of them you have to choose. Of course, along with it you will choose the type of element that you will be employing in order to solve that problem, whether you are going to do a shell or whether you are going to do a membrane or whether you are going to do or whether you are going to use a solid element and so on. So these are some of the other things that you will also consider, okay, apart from the type of analysis and so on. Of course, when there is contact, you will do also contact analysis, and that will complete to a certain extent. To a certain extent, there are other issues that you have to look into before you can actually do a finite element analysis, but this to a great extent completes the picture. Now let us go into the theory of finite element or nonlinear finite element analysis. That the theory of nonlinear finite element analysis also moves in a very, very similar fashion. What is that movement, or what is that we are, or how is that we solve a nonlinear finite element problem? Basically, if you look at it in very loose terms, I can say that nonlinear finite element analysis consists of a number of algorithms. A number of algorithms. Algorithms to solve a nonlinear equation. This can be the most popular among them being a Newton-Raphson scheme. You have other schemes as well, BF, GS and so on, but 90% of the problems are solved using Newton-Raphson scheme. So this is an algorithm for solving the nonlinear equation. So this can be employed whatever be the problem. Now you have for solving NR or Newton-Raphson scheme for solving the nonlinear equation. Now you have algorithms, or I would say formulations which would take into account incompressibility. So, formulations for incompressibility. Now, again, whenever you face incompressibility constraints, okay, whatever be the type of material property, you can use this kind of formulation for incompressibility. It can be selective reduced integration, or it can be a mixed formulation, or whatever it is. Okay. You can employ that technique right across. Similarly, we will have certain considerations including kinematics for taking into account a large deformation. The way we are going to, in other words, we may look at what is called as updated Lagrangian, we are going to look at total Lagrangian and so on, okay, which becomes important when we are looking at finite deformation. Again, this is common to whatever be the type of material behavior or whatever be the type of element that you are going to do, okay, they become or they are common to it. So, you pick up one algorithm from here, of course, there has to be certain small compatibility issues. You pick up one from here, and you can say whether total Lagrangian or updated Lagrangian and so on. Okay, you can, that also can be used to solve, this can be looked at as a very general algorithm procedure to solve problems independent of the type of material behavior. And of course, you have contact, and contact is looked again as from a very independent angle, and contact algorithms can be used for solving certain problems. Of course, it is not that you just, it's a plug and play, it is not that you just pluck one from here, one from here, one from here, whatever be the consideration, combine it and get an algorithm. It's not like that. There are considerations. For example, in contact, not all algorithms can be used for large deformations. Okay, there are algorithms which can be used only for a class of problems. Okay, when the sliding is large, then you can't use it, and so on. But still, once that class is clearly put, what is a class of problems that this algorithm can solve, then that is what you should look for in order to pick that up to get to your solution. Okay. So, with that in mind, let us now quickly go into the solution procedures for the nonlinear problems. Now, in fact, if you had noticed, I had not really rigorously defined nonlinear problems. I know I have appealed to your field to say what is nonlinearity. I have not yet defined mathematically what is nonlinear problem. All of you know, looking at it, yes, if it is nonlinear elastic, it has to be a nonlinear problem. If it's going to be elastoplastic, you know that it is going to be a nonlinear problem. But I have not rigorously defined what is nonlinearity. Where does that term come into, from where that term comes into the picture, especially in finite element analysis. The definition is not very difficult. All of you know the very fundamental definition or fundamental equation for finite element analysis. So, what is the equation for general finite element analysis? Most fundamental equation? No, ultimately what you solve. Yeah, KD or KU is equal to F. Okay, this is the fundamental equation we solve, and when we solve that, all of us know from our earlier fundamental finite element that determination of K is one of the major issues in the element formulation, and that we see that this K is independent of the, what is the assumption that we make ultimately when we get this formulation? K is independent of the D that it goes in. Okay, so K is not a function of T. Okay, you solve the problem only once, you apply the load, you solve this K straight away, so use the K, solve this equation for D, okay, by whatever be the procedure. Okay, right from precondition conjugate gradient or use Gauss elimination, whatever it is, you solve this problem. Now, the difference is in this case is that this k is not a constant. In a nonlinear problem, this k is no more a constant. So, this k depends upon the deformation. So, this k depends upon the deformation. So, I can't, in other words, I can't determine. So, once I say k, say a function of d, okay, say displacement, okay, and then put d is equal to f without even doing finite element analysis, without even knowing finite element analysis, you're going to ask me how are you going to determine k, right? It's not. So, you have an equation which becomes nonlinear, okay, and you can't solve it the same fashion as you did here.
Depend only on d, or like suppose if it is like fatigue one, k may reduce or increase like that.
Yeah, please, the question is, will k depend only on d and how it depends on d? This depends upon the problem. In fact, the major issue here is, like in the previous case, calculation of k for different elements is an issue in the linear finite element. In this case, calculation of k for different material behavior is an issue, right? So, the whole issue here is the calculation of this k, but we are not going to write it in the same form, we are going to change this form nevertheless, okay. But the issue here again is that the formulation of stiffness, we are going to call that in a slightly different fashion. We are going to give a new name to it. We are going to call this as tangent stiffness. The reasons for it will be clear as we go along, but this k is a function of deformation, and how it is, what function is it, how does it depend upon it, how will it vary, all these things we will do it. Is it clear? So, right now I am not going to define that, okay. The question that you may ask is it only a function of deformation alone? It may also be a function of damage. Suppose you are looking at damage mechanics. Say for example, you are analyzing concrete or composites, okay, and then there is a damage in the material. Then k definitely would vary, okay. So, you can of course say that damage is due to deformation, and so in one sense k is a function of deformation. So, that is why I said that k, okay, can be a function of d or another parameter which is again a function of d, and so on. Is that clear? Okay, we are going to, anyway we are going to see quickly, the whole idea is to quickly get in and see how we are going to solve these problems and get to know the whole issues of nonlinear analysis by using a one-dimensional case. So, the first and foremost lesson, yes.
In nonlinear analysis, we have the k independent of d only.
In the linear analysis, we have k independent of t.
Is there any kind of problem where k is dependent of time also? Dynamic?
Yes, k may depend upon time. K may depend upon time, but ultimately time. No, it would, because if you say that k depends upon time because of deformations, again it becomes the nonlinear problem. As long as k is not one factor, okay, and k depends upon deformation by some means, we are moving into nonlinear problems. Okay, we will see that as we go along, how k would depend upon and so on. Just maybe we'll take a couple of classes or more. Okay, let's first look at the procedure. The first difference, the major difference between a linear problem and a nonlinear problem is that we are going to resort to an incremental iterative approach. Iterative approach for solving this nonlinear problems. Incremental iterative approach. Now, incremental iterative approach has come about because of the type of algorithm we are using, of course, Newton-Raphson scheme and so on. Okay. But let us first understand what we mean by this term. Okay. Then we will look at the equations which govern incremental iterative approach. What it simply says is that since k is a function of d, I can't apply the force, all the force straight away. What it simply says is that I have to apply the force in an incremental fashion. That means that if I am given 1000 newtons, I don't apply all the 1000 newton at one go. I will apply 10 newton, I will apply 10 newton or 100 newtons initially, okay, make the body or component to come to equilibrium with that load, then increase that load maybe to 200 or 300, then make the body again to come to equilibrium, and so on. So this is what we mean by an incremental approach, where I keep incrementing the load. What is iteration? So as and when I increment the load, I iterate, or in other words, get better and better displacement quantities or displacement measures, so that the internal forces are equal to the external forces, or in other words, the body is under equilibrium. So I keep iterating so that the displacements are good enough for me to develop stresses which can hold the external forces. This is what we mean by an incremental iterative approach. So in other words, we have two big loops. What are these two big loops? One is that I will keep increasing the force or external forces, force incrementation, till we reach the final figure, and within this force incrementation I have an iterative loop, so that for the force given, okay, I get a good value, or good in the sense that the correct value of displacements, so that equilibrium is maintained. Okay, this is what is meant by an incremental iterative approach. Is that clear? Yeah. So now,
Sir, but in reality, we are not applying the load step by step. Will it reflect the real situation?
so whatever it is, ultimately, in reality, the question is, in reality, we do not apply loads like this. Okay, maybe if I want to apply 100, then I will apply 100. But whatever it is, please note this carefully, and please note what is the difference between a static problem and a dynamic problem. Right now we are talking about static problem. When I say static problem, then time is not a factor. Okay, it is, we do not consider inertia forces. So I apply this 100 Newton or 1000 Newton, whatever it is, and I do not invoke that inertia force. MA does not exist. Okay, it's so small that you neglect it, right? And keep applying the load, and your final interest is at the point when whatever load you had applied is under equilibrium with the stress. Is that clear? So it won't be any different as long as the process is static. But when will that have a difference? Suppose it's dynamic, I go and hit, okay, then it is a dynamic process, then I can't do it obviously as a static problem. Okay, in that case, I will automatically make a mistake if I do it as a static problem. Is that clear? Okay. So with that in mind, let us now develop a simple equation using Newton-Raphson procedure, and first do a one-dimensional case to understand this problem. So what is that we have? We have two things. One is an external force and another is an internal force. These are the two things that we have. Okay? Let us say that the external force is given by F and the internal force is given by P. And we know from our earlier classes or earlier study that P, which is the internal force, can be written as, do you remember? No. From a finite element perspective, you can write this down as yeah, no, this is B transpose, yeah, sigma d omega or dV or A dA, whatever it is, d omega, B transpose sigma d omega. In fact, if you remember, it is this sigma which, when replaced by means of stress strain relationship and then strain displacement relationship, gave rise to our K, because sigma can be written in terms of d epsilon, epsilon can be written in terms of bu. So, B transpose dB u is what we got, and that is what we obtained K. So, B transpose sigma d omega is the original or the internal forces that would be developed due to an external load F. So, at any point of time, obviously F minus P should be equal to 0. Note that I am not correct in writing just P, actually it has to be a vector quantity. So, in order to distinguish that from a scalar quantity, I will put a small squiggle underneath to just say that these quantities are vector quantities. Obviously, I can't write it in bold letters, so I am just putting that, okay, and you know what the size of these vectors are, or if it is a second order tensor, you know what these things are, and so on. So, F minus P is equal to 0 is the equation. As I had already told you that it is not possible for me to get that internal force straight away, okay, because of the fact that sigma now is not just d epsilon, that d itself is a function of epsilon and so on. So, I can't write it like K, like what I had done at that point of time. So, I have to, or I will definitely end up with an error or residue. This is what we call as residue. So, the whole idea here is to make this residue go to 0, actually not 0, but to a very small quantity. The residue, what is residue? Residue is actually the error, okay? That is the difference between what has been applied and what has been realized, okay? So, that residue has to be a very small quantity, right. Now, before we go further, a small introduction to terminology, because especially when you use finite element software packages, the software packages do not or may not, I should not say do not, but may not use just increment of load, but they would talk in terms of time. Most of the softwares talk in terms of time, application of or incremental load or application of loads in terms of time. Now, note that this is a point of confusion, basically because, as our friend here asked, now time, is it a factor? This is a static problem. Many users of finite element get confused when they see time as one of the factors, okay, because in a static problem, where do I get time? So, how do I handle it? Actually, the time that you have in a static problem is just a pseudo time. There is no, the interpretation is not the same as that you see in a dynamic problem. It is just a pseudo time. So, in other words, time is a carrier of force. What do I mean? I can say that, let me apply all the load in 1 second, say 1000 newtons in 1 second. Okay. Instead of saying that at every step you apply 100 Newton, okay, which becomes cumbersome when you program it, what these softwares do is to say that increment it in terms of 0.1 second. Okay. So, when you say that you increment by 0.1 second, 10% of the load is applied in the first step. So, 100, Instead of saying increment it by 100, second step increment the load by another 100 and so on, you say that let there be a time step with delta t is equal to 0.1. It's much easier to handle. So whenever we talk about time in the static analysis, understand that they are used as a carrier for the force. That's all, nothing more to it. Is it clear? It's usual to call that as say T, and that T is incremented, and so it is usual to put a subscript here as n. So T would start at T1 like what you do in a dynamic analysis, or T can start at T0, then T0 can increase to T1, where T1 is equal to T0 plus delta T and so on. So you can write down that equation, okay, as Tn plus 1 is equal to Tn plus delta T. That's the time factor. So n plus 1 is an incremental step. Is that clear? It's an incremental step. So say for example, if t is equal to 1 second, as I told you, it doesn't matter. You can have t is equal to 2 seconds and say let my time step be 0.1. It's the same as saying that t is equal to 1 second and time step is equal to 0.5. Okay, it's the same. So here, for example, if I start with t is equal to 0, which you usually do, okay, then Tn is equal to 0. So T1 becomes 0 plus delta T, which is say 0.1. So T1 becomes 0.1. T2, which is an increment over T1, now is 0.2 and so on. Right? Note that this delta T need not be a constant, or no software will have this delta T to be a constant. See, actually, you given a choice, you are not interested to do this. You already realize that this is going to take enormous time, computing time. What is that you are actually doing? You had a nice equation in the linear case, one nice equation like this. Okay, you're going to develop similar equation for every increment. Okay, and you're going to solve this 100,000 times, maybe 10,000 times. You're going to solve the same thing. You can immediately see the enormity of the problem, and you can immediately see the type of time you're going to spend before the computer before you can get a result. Right? So the smaller the delta T, the worse you are, because you have to solve that problem so many more times. Okay? So most softwares will not keep this delta T a constant. So what would they do? They would keep galloping this time step. They would keep galloping. That means that they would start with 0.1. If things go well, then they would watch for maybe one more step. Then they would raise delta T to be 0.2. If things go well, that means your convergence is good. They will gallop that again, maybe 1.5 times or 2 times or whatever software decides. Okay, then they will keep galloping it. So delta T is not a constant. At the same fashion, they will do the other thing also. Suppose you put 0.1, and in the iterative process, I said already that in the iterative process, I have to get convergence. What is convergence? That means your internal loads or internal loads developed by your stresses, which is P, and external loads, they match. Okay, that means the error residue is very small. If this residue is not small, even after very many number of iterations, okay, usually you put a limit. Usually it so happens that if it does not converge within say 16 iterations, okay, or 20 iterations, you are not going to get convergence that easily. That means your time steps are large. So what the software does usually is to cut down delta T. So if it had used 0.1, then it would realize quickly that look, at 0.1 I am not getting convergence, so I'll cut it down and go back to 0.5. Why this convergence does not happen, we will see that okay, as we go along. But so the delta t is not a constant, it can gallop when things go well, can increase, or it can be made to reduce or cut down. We call this as cut downs in time steps, and so that would happen. So it is not correct to write just delta t alone, but put one delta t n as well. Right? Is that clear? Okay. Now I will bring that to this equation and write this as, so psi n plus 1 is equal to f n plus 1 p n plus 1 should be equal to 0. This is the equation I have to solve, and this equation is solved by, so this is not going to be 0 first, so I will remove that. So the equation is solved by an iterative procedure. Very standard technique, this iterative procedure, very standard technique for solving any nonlinear problem. Okay, and Newton-Raphson, probably many of you would have studied this in your numerical analysis course. That's exactly what we are going to apply, nothing very different from it. So what do I do in order to apply Newton-Raphson technique? I start with psi n, okay, and get a better estimate of psi n, okay, by what is called as linearization procedure, or looking at the first term, linear term of the Taylor series. Okay, that's all we're going to do. Okay, so this is called classically as linearization. Okay, so that I can write the psi, say k plus 1. Look at that k I'm introducing here. I'll just come back to it in a minute. Is equal to psi k n plus 1 plus dou psi by dou u. Why u? It's obvious that this and this are functions of u or d, however you want to call it. Though this we had called this as d. D is the matrix, okay, u is the displacement, and d is the matrix which consists of displacements. Okay, we'll follow that u. Okay, so obviously this is a function of, this may or may not be a function of, for the time being let us say that that's a constant. Okay, it may or may not be a function of u. P is obviously a function of u because p is a function of sigma, sigma is a function of u, and so on. Epsilon, epsilon is a function of u, and so on. So this is a function of u, and so psi is a function of u. So dou psi by dou u, okay, and so that k remains, right, k remains into du, this is n plus 1 du k at say n plus 1 is equal to 0. Or you can, in fact, it's better to write that as n because that will be easier to follow later. So that this is the crucial or crux of the whole of nonlinear finite element, nothing else. If you understand this equation, okay, quite clearly, then you can understand the whole of nonlinear finite element analysis. Whole game is to solve this equation. Of course, this won't be actually equal to 0. Why? Because there are other higher order terms, we have left them out, okay, and so this is a truncation that we have introduced, okay, and we do not know the pattern of psi and so on, so we can't write that equal to 0, so it's approximately equal to 0. In other words, these k's indicate what? The iterations. So we march in two regions. One is first in n, that is increment, another is in k iteration. Is that clear? Okay. So solution of this is very straightforward, it's not very difficult. So how do I do that? Look at that carefully. dou psi k by dou u n plus 1. Look at this. So what is dou psi? Look at this and look at this. So what is this?
Dou f by dou u.
F, I had already said that it is independent of,
Okay, then 0 minus of
yeah,
p by dou u by
minus dou p by
dou u.
dou u. Okay? So this term is minus dou p by dou u. So in other words, in fact, this itself can be used to solve. Okay? So this can be written as dou psi into du, which is the increment. What is this? This is the increment in u with respect to the this particular iteration is equal to minus of this quantity here, okay? Oh, sorry, the residue in the previous case. So this combined with this equation, I get, or this can be looked at as minus dou p by dou u, okay, at n plus 1. Okay, and call this as kt, which is the tangent stiffness, what is called as the tangent stiffness matrix. Tangent stiffness matrix. Okay, and that when substituted back into that equation gives rise to what? This equation, when you substitute it here, gives rise to an equation of the form kt into du. Let me remove all these things for clarity. You can put it back again. Kt into du is equal to psi, that is p minus f. Okay, p minus f. Of course, you can write this. Please note that instead of this, okay, this minus can be removed here. Okay, this minus can be removed. Kt can be just defined as dou p by dou u. Either way, you will get the same result. Okay, or in other words, you can start with p minus f, in which case you will actually, if I define kt to be just dou p by dou u, if I define if kt is dou p by dou u, then what would be the equation I will get? Kt du is equal to f minus p. Okay, anyway, that minus sign and plus sign is quite clear. It's very simple to where you start with will matter or will decide what's the type of signs you have. So kt, the tangent stiffness matrix, is the core issue in nonlinear finite element analysis. Like you had k, which is the core issue in nonlinear finite element analysis, here kt is the core issue. How am I going to solve, or how am I going to get kt? Now once I get kt, my worries are solved, because I can solve this equation and get duk and build up on duk. So in other words, I'll just remove this and say that once I solve this equation, I can get down to writing u at n plus 1 at say k to be, that is at the end of the kth iteration once I solve this, to be, how do I write this? un plus sigma I is equal to 1 to k du k n. Please again note that this n plus 1 and n, okay, there can be a confusion because people may start put here n, here n minus 1 and so on. I think that should not be a confusion because when we write down completely, okay, the procedure, things will become very clear. So this is what we would also call that as delta u, okay, delta u k, okay, that we are going to calculate. That is the sum of du's, sum of du's as we proceed in iterations, right? So it's quite, I hope it's clear. Is there any questions? Clear? Okay. So once I know this ukn plus 1, okay, and I know un, of course, what is un by the way? Un for the nth time, the converged value. Of course, when I start, it's going to be 0. If I am in the 5th increment, un is the converged value at the end of the 4th increment, right? So this is the end of the 4th increment. So here, suppose I am in the 3rd iteration of the 5th increment. Suppose I am in the 3rd iteration of the 5th increment. Then what are the factors that will be involved? U, no, it won't be u2, you will be u4 plus, I had already calculated du for this, so this will be du1, okay, du1 at the 4th, that is 4th to 5th, okay, when I'm going from 4th to 5th, okay, so that one, or if you want you can write that as 5. How you do that is in your thing, and then plus du2 plus du3, that will give you 5th one. The previous converged plus what you have calculated in this current increment, okay, this iterations. It's customary to put n. If you want, you can also change it to be to n plus 1 and say that this is 5. That won't change anyway the result as long as you understand things. Okay, basically why? Because you may start with 1, so t is equal to 1 or n is equal to 1 is where you may start, in which case u2 will become u1 plus the results of the first increment. So you will get 1 here. So you can put either 5 or 4, that won't cause any confusion, okay, as long as you understand that in the current increment, okay, as I go from 4th to 5th, what are the changes that I see in du's. Now once I come to this step, it's very simple. Then I calculate epsilon based on these results, strains. Then I use constitutive equation to get stress. And then what do I do? I would check or I would calculate P. So from here, I would ultimately get sigma actually. Okay, sigma, which would now be tested against F. From this sigma, I would go and get P. Say, let me call this as P5 at the end of the 3rd iteration. Now I would check how good is this P35 when tested against external force. What is that? F n plus 1, that is F5. F5. How good, or what is this difference, or what is the residue?
Anyway, that F is going to be constant.
Exactly. Fi is going to be a constant. F varies only with respect to n. Fi would be constant. So what really happens is that I will keep increasing this p, so that I will approach f. Let us give a very graphical procedure for this whole thing in a minute, okay, so that we understand what we mean by this whole procedure. So once I see that this difference here is small, okay, I say that this small is again a word which we have to be careful. We will define it. So once we understand this whole thing, we will put down this procedure very neatly, and then you will understand what we mean. Small means it's not 0, but it's a very small quantity. Okay, what is small is also important. Okay, suppose I do a problem in Newton meter. Okay, the residue may be one value. Suppose I do the same problem in mm, the residue may be another value, and so on. You have to, it has to be independent of what you're working on. So you have to be very careful in defining what is the small. We'll define that again. Okay, and so once it's small, we say that convergence has been achieved. Then we go back and go to the next iteration, sixth one. Increase the load, exactly. If not, if this fellow is not small, what do? I get back to here, next iteration. That means I recalculate. What do I recalculate? No, look at that carefully. That is what is that called as? Correct. It is the tangent stiffness that you recalculate. Okay, then again calculate du, solving this equation. Okay, and then again do it. Now again look at the problem.
What is the sigma?
Sigma is the stress which you can calculate.
Calculate P.
Yes, because sigma is related to, we calculate from sigma, we calculate P because we defined. No, it's not minus. This will lead to, this difference or residue calculation. Is that clear? Note this again. In fact, the problem dimension is tremendously increased. Now, every time I do this in a Newton-Raphson scheme, I form tangent stiffness. Forming tangent stiffness takes time. Then I solve this equation. Okay, so in every iteration, I solve an equation, or in other words, every iteration is just equal to that of linear problem. So it is something like a linear problem. So if linear problem takes a second, this you can understand how long it would take. Is that clear? Okay. So that is why nonlinear problems take tremendous time. Not only incremental approach, but also an iterative approach. So tangent stiffness, every time when you form it, that takes time. Yeah, you can modify it a bit. We will do that graphically, maybe in the next class. We can modify this procedure a bit. Call this as modified Newton-Raphson. You will understand that once I put this whole procedure for a one-dimensional case in a graphical form. Okay? So essentially what is that we did? Just to summarize what we did, we looked at residue. Residue was defined as the difference between the external and the internal, or internal and the external forces, difference between them. Then we linearized this residue, arrived at an equation by truncating to the first term, Taylor series approximation. From this, we developed, or we came back to our very familiar simple simultaneous equations, defined tangent stiffness, solved it. Okay, for every iteration, we keep a watch on this residue. If the residue happens to be very small, we said that we are happy with it, go to the next step, and so on. We keep repeating these steps until we finish the problem, or when t becomes t total, say 1 second, what we had defined before.
So what exactly basically changing in tangent stiffness in the successive iteration?
Yes. So what is changing tangent stiffness? What do you understand by tangent stiffness? This is exactly what we are going to see in the next class. We will see it starting with a graphical procedure. We will see what exactly do we mean by this term tangent stiffness.